Okay, this is lesson 17 and I am topic 2, but it is rational functions and not polynomial functions. So something to note is that I call it the dirt, and I don't even remember where I heard that, but distance equals rate times time. So you can manipulate this equation to give you other information. So if you divide both sides by rate, your rates cancel and you're left with distance over rate is time. You can do that same with the time. So when we are looking at this, I think you'd say Kieran, his aunt plans to bike 10 miles. How long does it take if she bikes at an average rate of 8 miles per hour? So we know the distance is 10, and we know she's going 8 miles per hour for however long it is. We can divide both sides by 8, which is going to give you 1.25. So 1.25 hours, or 1.25 hours. Be careful if you convert this. This is 1 hour and 15 minutes because a quarter of an hour is 15 minutes, not 25. We could, instead of starting in this format, because we already talked about this, we could have just gone straight to 10 over 8 to give us our time, but that's okay if you didn't. So how long will it take if she bikes at an average rate of r miles an hour? Well, again, we know that our distance equals rate times time. So that leads us back into this, where when you move this, it'll be 10 over your rate equals your time. Again, these are all going to relate to these equations right here. So he wants to join his aunt, but he only has 45 minutes to exercise. What will their average rate need to be for him to finish on time? Because we're measuring in hours, you're going to want to convert 45 minutes is 0.75 hours. And I don't write my 0 in front of my decimal. You definitely can. It's just partially me being lazy. So when we do this, we know that we are going to have our 10 miles. We have 45 minutes to do it, which is 0.75 hours. And that will tell us our time. So when we plug this into the calculator, 10 divided by 0.75. Let me see here. We get 13.3 repeating. Haha. And here's where I messed up. This should be my rate. Because I have 10 is my distance, but I was dividing by time. So it's the opposite of what I did up here. So be very careful and make sure you know what it is. Now my answer is still the same, but the difference is if this was time, it'd be 13 hours. And that didn't make sense, which is why you double check. It is your rate. So he's going a little over 13 miles per hour to get that workout in 45 minutes. What will their average rate need to be if they have T hours to exercise? Well, you have your distance is your rate times your time. Well, if you divide by your time, that equals your rate. So because I was nice and wrote those 3 out ahead of time, that told us this question and this question, but you could determine it with how we solved these both times. Just a quick note, if we want to set this one up, it would be like 10 equals 0.75 r, and then you divide. 17.2 continues along the same problem. We have the same equations, I just didn't write them all out. Distance, rate, time. Write an equation that gives his time in hours as a function of his rate. Well, we know that our time with regards to rate is going to be our, so we're solving for time, is our distance over our rate. So what goes right here is your variable that you're going to see on the other side. You see this a lot with f of x and then x on the other side. That's function notation. So when you see this word function, you're going to have the function name or the variable, whatever represents, parentheses, what you are regarding. So the rate r. When we graph it, that was a very crooked line. Let me fix this. Okay, so when we graph it, we are not going to worry about the negatives. So what I mean by that, this is our time. I'm going to make sure I do this right. This is my time. This is my rate. When, and technically this is T of R. This is like your Y. This is like your X. Okay, we're just using different letters to represent. The slower your rate, the more time it's going to take. So if you're not moving, it's going to take forever. We're obviously not going to mark that then because it doesn't make sense to go 0 miles an hour. But generically, it's going to be something along these lines. We can't have negative time. And we're not going to have negative distance, which takes out all of that. So we are just looking at this quadrant up here. That first quadrant. Again, the faster you go, the less time it's going to take. So the meaning of T of 8 is how long it takes to bike 10 miles going 8 miles per hour. The same numbers we saw in 17.1, so we already know the answer to this, but this is putting it into context now. So explain your reasoning and how you know. Well, we're using T of R, which is time in regards to rate. So if you know how far you're going, your distance, and you divide by how fast you're going, that tells you your time it's going to take. T of 0, does that make sense? If you're plugging in your rate equals 0, here, I'll put rate equals 8 up here so I don't forget. Rate equals 0. You're not moving. And even if it's a stationary bike, you're still going to accumulate those miles. So no, it doesn't make sense. Because you're not moving. You're biking. You're trying to get 10 miles in. If you're going 0 miles an hour, it does not work. So as R gets closer and closer to 0, so if we look back up here, as R gets closer and closer to 0, what's the behavior of the function tell you about the situation? So the slower you go, or the slower he goes, the more time it takes. And this, a lot of times I compare this to a car. If I'm driving home and I'm driving slower than the speed limit, it's going to take less time than my GPS tells me, or less time than it normally takes. The next question is, as R gets larger and larger, so as you go this way, you're going a faster rate, what's it tell you? So the faster he goes, the less time it takes. So if I go over the speed limit, I'm going to beat my GPS. I'm sure quite a few of you watching this have seen someone who plays the race the GPS game, and you try to take off time, right? Not necessarily safe, but something that a lot of people do. And this relates to that context. So I'm not going to talk about 17.3 because that is a card sort, but we are going to do some practice problems. So in practice problem 1, Jada's planning a kayak trip. She finds an expression for the time T of S in hours it takes her to paddle 10 kilometers upstream in terms of S, the speed of the current. And we're using kilometers per hour. So this is the graph she gets, and we're looking from 0 to 7.5. What would be the more appropriate domain for Jada to use? Well, we're looking at time. We're not going to have negative speed, and you don't want, we're just going to stick with, you don't want negative speed. So we're just going to scribble this out. Because of this dotted line right here, you see it doesn't really cross this line. So more appropriate domain for Jada to use would be like 0 to 5 or 0 to 5.5. So we're going to say 0. And actually, normally I would say equals, but we're just going to use less than, because if it equals, yes, technically you can go 0 miles an hour or kilometers per hour, sorry, but I don't think that's smart. Okay, so we're going to say S, and then we're going to say less than or equal to 5.5, or just less than. you're going to see in later lessons, this is called an asymptote. That's a number we cannot reach, so you can't use an equal here. Again, I'm not using an equal here because even though it has a point, it doesn't necessarily make sense to go 0 miles an hour unless you're anchored down. Again, 0 kilometers per hour. I'm going to write kpm up here, or kph, so I don't keep forgetting. What's the approximate speed of the current if her trip takes 6 hours? Okay, so again, we know distance equals rate times time. She's going 10 kilometers. She's going some rate that's going to take her 6 hours. So if we divide both sides by 6, and we do 10 divided by 6, which is what, 1.67? Let me double check that. Yep, 1.6 repeating, or 1.7 or 1.67. I'm just going to say 1.7. So she's going 1.7 kilometers per hour. I got the label right that time. Okay. I am not necessarily a huge fan of volume in these situations and with rational functions, but if you look, you have that your surface area is 12 over your radius. So as r gets closer and closer to 0, you're going to have a smaller radius. Which is going to give you, I'm just double checking here, a bigger S of r, which is your surface area, right? Side. Area, yeah. Okay, if you notice when I do word problems, like I did in the prior one, sometimes underlining or highlighting, if you want to highlight, helps keep track. And you are watching me do this in real time. So you see the mistakes and the struggle that sometimes it takes to pick out this key pieces of information. These key pieces of information. Apparently English is not my strong suit today. When you do it, read through it several times. Read through it once, just once, regular. Read through it again to find the detail, and then read through it again to see if you missed anything. Okay, so bigger area. Because you know it's going to equal this 12. My example is if you have a radius of 1, that leaves you with 12. But if your radius is 6, that leaves you with 2. So that's the difference. So the bigger your r is, what you're dividing by, means actually the smaller. So that's what's going to be this one. So if you have a bigger radius, you're going to have a smaller area, or S of r. And again, use these examples. If your radius is 6, your area is only 2. But if your radius is 1, your area is 12. Okay, so you are going to see this word asymptote, and I didn't know if I wanted to discuss it in this lesson or different. But the example I use for an asymptote is when little kids do that, and I'm going to use my pencil. When little kids are like, I'm not touching you, and they get super close, and it might look like they're touching, but if you turn it, they're not actually touching. So like really close, but not actually touching. That's an asymptote. Your line is going to get super close, or your graph's going to get close to the line, but not actually touch it. Oftentimes, like if these are your axes, they're represented by dotted lines. So these are just examples. Now, they're not always represented by dotted lines, but what you can see is like they get really close to those lines and not actually touch them. So this would be your horizontal asymptote, and this is your vertical asymptote. The confusing part in my mind is that a vertical asymptote is when your denominator of your fraction equals 0. And again, that's the bottom part of your fraction. And that's going to happen at an x value. So x equals some number. So it's vertical, but it's when x equals something, because if this is 2, your vertical asymptote is at x equals 2. That means your x value is always 2, which is why it's straight up in that line. Your horizontal asymptote is going to be y equals some number. Because if this is my, like, y equals 2, y is always 2 no matter my x value. So when we look at this, our vertical asymptote is the denominator. So we set x minus 1 equal to 0. we solve it, we get 1. Because if you plug in over 1 minus 1, you get 6 divided by 0, and this is going to give you an undefined number. So if you plug that into the calculator, it will pop up as undefined or not able to calculate or something along those lines because you can't divide by 0. So here we go. We will talk more about horizontal asymptotes in a bit. Just as a piece of advice or for future reference, 6 over x minus 1, you can break it up into 2 pieces. And this I'm going to go do in order. 6 over x minus 6 over 1. And this right here is going to help you find your horizontal asymptote, and that's what we're going to talk about in lesson 18.